Today I'm going to be discussing propositional logic. The foundation of propositional logic are logical connectives. These are words or symbols that connect statements together. For example, the dog and the cat ran away. The logical connective here is the word and. It is connected the same as the dog and the cat ran away. Or is also another logical connective. So I saw either the mouse or the rat yesterday. And if then is another logical connective. So if the moon is made of cheese, then my favorite food is pizza. The common logical connectives are conjunctions, disjunctions, negations, and implications. Now, suppose we have two statements, A and B. We can write A and B by writing A and then an up caret B. So we have A and B is true when both A and B are true. Disjunctions can be wrote by writing A and then a down caret, which will represent or B. So A or B is true when either A or B is true. Negations, we can write this little bar-like symbol in front of the letter. So we have not A is true when A is false. And we'll come back to implications in a bit. Now, truth tables are a method of organizing all the ways that a statement can be true or false. The common truth tables are P and Q, P or Q, and not P. So let's take a look at just these first two columns in the first two tables. These are just the different ways we can have P and Q be true. As we can see, both P and Q can be true. Just P can be true, just Q can be true, or neither of them can be true. And these are the only ways that they can possibly be true and false. Let's now look at the second part of the table. As we can see in the first one, we have P and Q. And we can see that it is true so long as both P is true and Q is true. This is definitionally what it means for two statements to be true connected with an and. We can look at the second table to see that P or Q is true so long as either P is true or Q is true. If they're both false, however, then P or Q is false. Once again, this is definitionally so. This is how laws of logic have been defined. And then the last table, we have P, and we can see that negating P just simply reverts the truth value. So if we have P being true, then not P is false, and if P is false, then not P is true. Once again, this is definitionally how logic works. An important idea in propositional logic is that two statements are logically equivalent if they have the same truth table. And this should make sense. If they have the same truth table, that means that whenever P and Q are true and false, whatever the statement is true or false, and it's exactly the same for both of these statements. And so, they should be logically equivalent. And we wouldn't be able to tell the difference between the statements because the output is always the same. Let's now discuss implications. Implications are generally of the form if P then Q, however they can kind of vary somewhat. We write it with P and this right arrow Q, and it is equivalent to not P or Q. We'll come back to why that makes sense later. The converse is if Q then P. It is not logically equivalent to the implication. And the contrapositive, if not Q, then not P, is logically equivalent to the implication. And we'll come back to why that makes sense later. For now, let's just look at the truth table for implications. So let's take this example. If I own a dog, then I own a cat. If both P and Q are true, then the implication is true. And this makes sense. We're saying if I own a dog, which I do, then I own a cat, which I also do. So we do expect the implication to be true. The second row, we see that we have P is true, so I own a dog, but I do not own a cat. Now this is false, and I feel that this is pretty intuitive. We're saying that I own a dog, but I don't own a cat. So clearly it is not if I own a dog, then I own a cat, because I don't own a cat. So the statement is false. This third line can be a little confusing. So if P is false, but Q is true, then the implication is still true. So here I own a cat, but I don't own a dog. The reason why it is still true is because the implication really is just saying, if P is true, Q by necessity must also be true. If that's not the case, then the statement is false. And that's why right here, we have Q being true, but P being false, that it's still true. And in this fourth line, it's the exact same thing. We don't really care if P is false. It's not a big deal. The implication is still true because we're not having this one false statement. The implications really are basically defined by this statement. P and Q must be true together, otherwise P cannot be true. That is how implications work. So here, let's look at the contrapositive, which is if not Q, then not P. So we have this new truth table, which you can see I added in a couple extra columns. This is just to help us understand why not Q, then not P does work the way it does. As we can see, the only time that it is false is when not Q is true, and when not P is false, which is the exact same thing that was going on in this truth table. As we can see, when P was true and Q was false, it was false. So they are logically equivalent. Nothing has changed. So why is it logically equivalent? Well, the reasoning is because when not Q is true, that means Q was originally false. And when not P is false, it was originally true. And that is that one instance where we just can't have if P then Q be true. It is false in that one instance because of how we, to the most extent, just define it. And that's why the contrapositive is logically equivalent. Let's now also go back to not P or Q. So here we're just going to look at this column and this column. So the Q and not P columns. And we're taking the OR of them. So basically we have Q is true or not P is true. And we see that, well, this is true. And so we have true. Let's take a look. We have Q is false and not P is false. And this not, and once again, we already know how OR works. We have, so two falses, we have a false. And then we have Q is true, not P is true, so they're both true, and we have Q is false and not P is true, which when we take the OR of them, it's true. So we can see that it is logically equivalent. And once again, this does make sense. Because if it's not P, that means it's false, and we already know that, well, it's already going to be true. So we're all good there. But if P is true, so which not P would be false, then we have to have Q also be true, otherwise it is false. So the only instance where not P or Q is false is when P is true and Q is false, which is exactly when if P then Q is false. Hence why they're logically equivalent. And you can see now that why it is so important that we do use logic tables to be able to determine if things are logically equivalent. Because we can see that these three different statements are all logically the same. Let's now move on to De Morgan's laws. This basically allows us to work with negation in logic. So we have two laws. Not P and Q is logically equivalent to not P or not Q, and not P or Q is logically equivalent to not P and not Q. The thing is, why is this true? It kind of seems counterintuitive. Like, why are we switching from an and to an or when we negate and? It seems a bit strange. So let's look into why these are true. Now, first, let's just take a look at the negation of P and Q. But to do that, we kind of need to know what the P and Q truth table looks like. So I have that up. And all we're going to do is we're just going to take all of these values in this P and Q column and change them to be the opposite of what they are. So this true will become a false, this false will become a true, this false will become a true, and this false will become a true. So, and there we go. So not P and Q has false, true, true, true. Now, we notice that we have three trues in one false. That's very similar to an OR. So maybe it does make a little sense why we're going to see an OR. And evidently, if we take the truth table for not P or not Q, they are identical. But why? Well, let's consider the statement. I do not have a dog and cat. Intuitively, we kind of have some understanding of what this means, albeit we're not fully logically focused on it. But if someone says, I don't have a dog and cat, we already know that this first line is false. Because, yeah, we know they don't have both. We intuitively already know that. However, I do not have a dog and cat does mean it's possible they do have a dog, or they have a cat, or they don't have either. And we can, even in conversation, we recognize that. You know, if someone comes up to you and says, well, I don't have a dog and cat, you may be like, oh, do you have a cat? Well, yeah, I do have a cat. And then you know, well, you can't have a dog. Let's now look at the negation of P or Q. So once again, we have the truth table for P or Q this time, and we can see that it's true, 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 false. We're just going to negate those values, and now we have false, false, true. And we can see right away that the only time that is true is when it is not P and not Q. And so it really is no surprise that not P or Q and not P and not Q are logically equivalent. However, on a more intuitive level, let's consider the statement, I do not have a dog or cat. When you hear that statement, you probably already immediately recognize, well, they don't have a dog, they don't have a cat, and they definitely don't have both. And so we already know that this statement must mean that they don't have either, so that's the only time it is true. This one is very intuitive, at least in this instance. And in general, a lot of logic kind of can be somewhat intuitive, because we do use it on a regular basis when we communicate. We do use words like and, or, and if then. We don't always use it exactly the same way that we would use it logically, but it is similar enough that this should feel somewhat natural, somewhat intuitive. Now let's move on to the negation of an implication, because we have some knowledge on negations. So, we have to recall that if P then Q is just logically equivalent to not P or Q, because we can easily find the negation of P or Q. It's not probably much harder to find not P or Q. So, not if P and Q is going to be logically equivalent to not P or Q. And of course we know that we just have to negate those P and Q and change that or to an and we suddenly have not P and not Q. Now these two nots here are a bit annoying. Now you might already think, and you probably already know, that they're just going to cancel each other out. And that is definitely true. It's just like how we have double negatives in language. We don't really like them because they can be very confusing and awkward. And so we are lucky that negating a negation undoes that negation and it's like nothing even happened. So, yay, we now have P and not Q. And that is the negation of if P, then Q. To conclude, I want to go over argumentation. Over here, we have a deduction or inference rule. If P, then Q, and P are both presumed to be true. These are true propositions. And when they are true, we can then conclude that Q must also be true. These three little dots mean therefore Q. We know that this is a valid deduction rule because of the truth table for if P, then Q. So, we know that if P, then Q is true. So there's only 3 rows where that happens. The first row, the third row, and the fourth row. We also know that P is true, which is only the first row and the second row. The only time in which both of these are true is in the first row. And it just so happens to be that Q is true. So, we can then conclude that Q must be true if we have if P, then Q, and P. Let's look at an example. If the store is open today, then I will go buy groceries. So we know that this implication is true. Then, we also know that the store is open today. So we can now conclude that, therefore, I will go buy groceries. Now that I've gone over the basics of propositional logic, I hope that you've been able to have a better intuition of how propositional logic works and one of the use cases for